Welcome to Engineering Python. This is a Python programming course for engineers. In this video, I will talk about how to use SciPy for solving simple optimization problems. Optimization aims to find a numerical solution to a minimization or maximization problem. SciPy.optimize module provides algorithms for simple optimization, curve fitting, and root finding. First, I will show you how to find the minimum of a function with a single variable. Before we start, we need to turn on the Jupyter Notebook renderer so we can see all the plotting results in this browser. We need to import pyplot as plt. We also need to import numpy as np. Now we define a function fx equals x squared plus 10 times sin x. Next, we generate 51 points for x. These points are evenly distributed between -10 and 10. This is the result. After that, we apply this function to x and get the corresponding y values. After all these preparations, we plot x and y in a figure. Turn the grid on to help us better see the curve. This is the curve that represents the function fx. Now we import SciPy.optimize module as opt. Let's find a minimum of the function fx using the bfgs method. bfgs is the initials of the full authors of the method. The function we use is fmin bfgs. The first argument is the function f we defined earlier. x0 equals 0. It's the initial guess. This is a search starting point. The algorithm will stop after it reaches the maximum number of iterations, 2000. This function returns the full output including the optimal x value, xopt, the corresponding y value, yopt, and so on. It shows the optimization terminated successfully. xopt is about -1.30 and fopt is about -7.94. We can plot the function first and then mark the initial point and the optimal point in a figure. This is the initial point. This is the optimal point. The search process is like we put a ball here and it will roll to the bottom. The initial point is fairly close to the optimal point. What if we have an initial point x0 equals 6? Let's try this program. The only difference between this one and the previous one is x0's value is changed from 0 to 6. It says optimization terminated successfully, but when we show xopt and yopt, they are different from the previous results. We plot them in the figure. This is more obvious. We started from here. Now we can only find a local minimum here. We cannot find the global minimum here. This is the limitation of the bfgs method. It can get trapped by a local minimum. We can try another method using base hopping. Base hopping is a stochastic algorithm which attempts to find the global minimum of a smooth function of one or more variables. Because of its stochastic nature, it cannot guarantee to find the global optimal. However, it may perform better than the bfgs method for some functions. The function we use is opt.basehopping. This is the function we defined earlier. The initial starting point is x0 equals 6. T equals 1. This is a very special parameter for the basehopping method. It's short for the temperature. A high temperature means larger jumps are allowed. Step size specifies the initial step size for use in the random displacement. This is the returned structure. The optimal function value is about -7.94. The optimal x value is about -1.30. We plot the initial point and the optimal point in this figure. This is the initial point and this is the optimal point. The algorithm can somehow jump over this local minimum and reach the global minimum. SciPy.optimize module can be used to solve equations. We use this equation as an example. fx equals x squared plus 10 times sin x equals 0. We use the fsolve function to find a root for this equation with the initial value x0. The root is x equals 0. Let's plot the initial point and the root here in the figure. This is the initial point, and this is the root, where the function f is equal to 0. If we change the initial value x0 to -3, the root is x is equal to -2.49. In this figure, this is the initial point, and this is the root, where the function f is also equal to 0. This example shows that the fsolve function highly depends on the initial value. Finally, let's see how SciPy can be used for curve fitting. Curve fitting is basically an optimization problem. It's a procedure for finding the best fitting curve to a given set of points by minimizing the sum of the squares of the offsets or the residuals of the points from the curve. I have an illustrative example here. Say we have 4 data points in this 2D space. We want to find a curve that can approximately go through all these data points. In this example, we find a straight line. We can see that the fitting is not so good because the offsets from the points to the line are still pretty large. In this example, however, we find a curve. All the data points are very close to the curve. The offsets from the points to the curve are very small. This curve is probably what we wanted. Let me show the x values we created earlier. X contains 51 numbers evenly distributed between -10 and 10. Y is the f function of x. It has the same shape as x. I plot x and y in this figure. It contains 51 data points marked by little crosses. Next, we add some random noises to the y values. The noise is generated using the standard normal distribution but amplified by 5 times. These are the y values with noise. Let's plot the original data points and the data points with noise in the same figure to compare. The original data points are marked by little crosses, and the data points with noise are marked by little circles. They are not the same but quite close to each other. Assume we know the structure of the function we try to fit, which is f2x equals a times x squared plus b times sin x. We need to determine the best values of the coefficients a and b. Let's define this function f2 with 3 parameters, x, a, and b. This is the function structure. Our initial guess for a and b are a is 2 and b is 2. Next, we use a curve fit function is a SciPy OPT module to do the actual fitting. It passes the function name f2, the data points x and y noise, and the initial guess for a and b. The result is parameters and estimated covariance. Let's show the parameters. The first one is a. It's 0.995, which is very close to 1. The second one is b. It is 10.59, which is very close to 10. Now we use the new parameters a, b, and the function f2 to calculate the fitted value, y fit. These are the values. We'd better plot them in a figure here. The data points with noise are still marked by the circles. The blue curve represents the curve we fitted. Although some points are still not located on the fitted curve, this is already the best one we can find using the given function structure. Okay, that was how to use SciPy to solve simple optimization problems. The course materials are available on YouTube and GitHub. You can watch the course videos in sequence. If you like this video, please subscribe and share. I'm Wang. Thanks for watching.